an intersection of probabilities. Okay, so what's the probability of this happening and that happening? But what we're now looking to do is, how do we do probability with OR? And we know that OR in set notation, if I said probability of A or B, it's the same thing as a union in set notation. So these two things mean the same thing. But the way we're going to do an OR probability is OR will imply that we're going to add the probabilities of the two events happening together. However, if these two events have anything in common with one another, we don't want to count those things twice. So what we're going to wind up doing is we're going to subtract out the intersection of those events. And as a reminder, that symbol would mean and. So we want to kind of avoid some double counting here. Okay? So if you look at this Venn diagram below, we have sets A and we have set B. And if I want to find the probability of A union B, that probability right there, the way we can develop this is by saying that we know now this is the probability of A plus the probability of B minus the intersection probability of A and B. And the probability of A happening is going to be, well, if we're assuming that these things are probabilities here, it's going to be the sum of P plus Q, right? That would all be contained within A. So this is the probability that A will happen, plus the probability that B will happen would be then Q plus R. And then from that, we're going to subtract the intersection, which is just Q in this case. You can see how Q is originally added twice here to determine the total probability for the union of these two. So to avoid that double counting, that's why we subtract the intersection out. And if I cancel one pair of those Q's, the total probability would equal whatever P plus Q plus R is. So if you had a Venn diagram and the probabilities were filled in, you could do it in either format. You could add the three probabilities that are given together, and that would account for what the union's probability is. Or if you knew the probability of A altogether and the probability of B altogether, then you would just subtract out the intersection there to get the total probability. So in this example at the bottom, a car is brought to a repair shop for service. The probability that it needs transmission fluid is 0.38. Probability that it needs brakes is 0.28. And the probability that it needs both is 0.16. Let the event that a car needs transmission fluid to be T and then brakes to be B. So what are the following values? We could do this pretty quickly based on the information. Transmission fluid replacement was the probability of 0.38. Probability we need brakes is 0.28. And then finally, the probability that it would need both T and B was given as 0.16. So just kind of quickly grabbing that information from this problem up at the top here. And then it says use the addition rule to find the probability that a randomly selected car needs transmission fluid or the brake pads replaced. So when you see that key term or, we know that it's the union of those two. So symbolically, we're finding the probability of T union B. And just to kind of get with the formula that we used from the start of today's notes, get a little bit more used to it, it would be the sum of the probabilities of each event, but then we have to subtract out the intersection. Okay, and luckily those are actually all the probabilities that we've already listed. So that would be 0.38 plus 0.28 minus the intersection of 0.16 for a grand total of, there is a 50% chance that if you go to get some service that you're going to need one or the other. And speaking from experience, I would say that's probably right on par. Every other time I go in, something has to be fixed. So, okay, just as a quick getting started there, that was pretty straightforward. We're given all the info already. Let's kind of see what this might look like in terms of some of the tables that we've seen. Okay, so in example 2 here, a small high school surveyed 52 of its seniors about plans after graduation. They found the data and wanted to analyze it based on gender. So you can see we have some data for males and females in the top 2 columns. And then we have going to college versus not going to college down here. And you can kind of see these totals going down. And if you take a look at this notation down in the part A, when it says n of m, that would be the number of, and then capital M, it's defined up there as being males, right? So if we look at male, female, college, and then not going to college. So the number of males total is 30 here, okay? So we can fill that in pretty quickly from the top. Number of females total, 22. Number going to college across the top row is 29. Number of not going to college is 23. And now what we're going to start looking at is some intersections and then this or statement at the end here. So the number of male and college. So just kind of trace across male and college intersect at 16 is the number there. We'll eventually relate this to probability in a little bit. The number of female and college. So female and college looks like it's going to be a total of 13. And then if I said female or college, you just have to be cautious here that this would be the number of female plus the number of college, but then you're going to subtract the intersection for the number of female and college, because we don't want to count female and college students twice in both of these groups. So we're going to subtract out that intersection. The number of female total was 22, plus the number going to college, 29, minus the females going to college, which is 13, for a grand total of 38. Okay, so out of the 52 people, 38 of the 52 would be people who are female or they're going to college. Okay. So part B, what is the probability that a person picked at random would be a female who is going to college? Represent this using a union or an intersection. So females going to college, if I were to connect those two different categories in this context, I would say that this is a female going to college is going to be an and statement. We want both of those things to be true. So symbolically, we're looking for the probability of female and college, which we actually know the number of females going to college is a total of 13. But when it's probability, I have to make this into a fraction now, right? Out of the total number of people who were in the survey, the total number of people, remember, is 52. So 13 out of 52 is going to be the answer to that, which can be reduced to 1/4. Okay, so a quarter of our students that are surveyed are females that are also going to college. On the other hand, what's the probability that a person picked at random would be female or someone going to college? Since we've already done the work up here, I'll say that we can actually just take the number of people who are female or college goers, which is 38, and then we could divide that by the total number of participants, which would be 52. That actually does reduce real quick to 19/26. So explain why the probability of female or college doesn't equal probability female plus probability college. And the reason why I'm hoping you would say here is that there's going to be some overlap there, right? So the females going to college are counted twice. And to avoid that double counting, that's why we're going to subtract out the intersection like we did up here. Okay, so you can't just simply add the probabilities together to get the or case unless certain criteria holds. Okay, so find the general law of probability based on part D. We've already talked about this, but the probability of F union C would be probability of F plus the probability of C minus the intersection of those groups. Okay, so again, whole idea of today, when you're doing the or problems, probability of this happening or that happening, we got to subtract out any overlap or any intersection there, which might bring us into the question, well, what if there is no overlap? And that certainly happens in certain scenarios. What if the probability that A and B happen, the intersection, what if that probability is 0? Well, the definition of that term would be that the two events are mutually exclusive. So when events A and B have no outcomes in common, the term that we're going to use to describe those is that they are mutually exclusive. So you can see in the last case that, yeah, the events of being a female and going to college, they're not going to be two distinct groups. There's going to be some overlap there. But in the real world, are there a lot of things that could be considered mutually exclusive? Sure. So in math class, the grade breakdown on the midterm were as follows: 7 A's, 12 B's, 3 C's, and 1 F. Sketch a Venn diagram of the situation. We haven't seen a Venn diagram that looks like this because usually Venn diagrams we're seeing sets that all intersect and overlap with one another. But I'm hoping you're realizing that there's no way you could have been somebody who got an A but also a B at the same time. Kind of impossible. So these would actually be 4 distinct sets with no overlapping at all. So you'd have set A with 7 people in it, set B for the B's with 12 people. I'm going to call set C 3 people, and then I'll define set F for the people who got F's to be 1 lonely person in that set. Okay, so not kind of the most exciting Venn diagram, nothing intersecting, overlapping. Find the probability of getting an F. Well, there's only one person who got an F out of the total number of people who took the midterm. If you add up 1 plus 3 plus 7 plus 12, the total number here is 1/23. Okay, next, what's the probability of A and B? So the probability of A and B of getting an A and then also a B is going to be 0. Can't happen. Okay, it's absolutely not going to happen. So then what would be the probability of A or B? Well, according to the formula for OR, we should do the probability of A plus the probability of B minus the intersection. But I'm hoping you're realizing that since these events are mutually exclusive, we're not going to have to subtract out that intersection. It's just going to be 0. There is no chance of getting an A and a B. So the probability of an A is 7 out of 23, plus probability of B is 12 out of 23, and we can kind of just stop there and calculate the probability. You want to write minus 0, go for it. But otherwise, the total probability of getting an A or B would have been 19/23. Okay. And then we have to be a little bit careful in part E. Part E is another OR statement. So the probability of B or not an A. So that would be the probability of B plus the probability of not A, which I'm going to write as A complement. Hopefully you're good with that notation. Minus the intersection of getting a B and not an A. Okay. So for this one specifically, probability of B we saw is 12 out of 23. The probability of getting not an A would be everything except 7. So that would be 16 of the 23. And if you add these up, I would hope you would see a big problem if you didn't subtract the intersection out, because 12 and 16 is 28 out of 23. There can't be more than a 100% chance of this happening in our class. So if I subtract out that intersection, what is the intersection of getting a B and not an A, if both those things have to be true? It's actually just subtracting out all the people who got a B again. If you want to be a B and not A, it's, well, everybody who got a B. So we're actually going to subtract out all those people who we initially added on anyway. So essentially what this turns out to be is it's the probability of not getting an A, which is 16 out of the 23 people. And finally, are getting A and B mutually exclusive? Absolutely, yes, right? You can't score A and B at the same time. And just a little bit mathy here for a second, if the probability of the intersection equals 0, then definitely those two things are mutually exclusive. Okay. A little bit more practice. I'm going to actually do this one with you guys, and then I'm going to give you some directions about the last page of these notes. So insurance companies typically try to sell many different policies to the same customers. At Hurley's insurance company, 56% of the customers have car insurance, 48% have homeowners insurance, and 18% both. I actually am somebody who does have my car and homeowners insurance with the same company. I'd be curious to see, like, if you check with your parents, I'm sure many of them do as well, because they try and offer you a kind of a deal if you go with all of your insurance policies with both companies. So if a customer is picked at random, find the probability that she or he has at least one of the policies. So at least one is going to be an or statement, because I could have the homeowner's insurance or I could have the auto insurance there. Okay. So let's see. Let's do a Venn diagram. So we have homeowners and we have cars. Okay. So I want the probability that you have homeowners or car insurance with this company, which would be the probability of homeowners plus the probability of car insurance minus the intersection there of H and C. Okay, if I fill in this Venn diagram, remember that you have to really fill in the middle part first. So the probability that they have both is 0.18 here. Sorry that I actually can't quite squeeze that in. But if the probability of having both is 0.18, subtract that out of the 56% to figure out the customers that have car insurance policies there. Okay, so 56 minus 18 is going to be 38% left in just the car insurance, but not homeowners with this company. And same idea, take 48, subtract out the 18, so you're going to have 30% of people who have just homeowners but not car insurance with the specific company. And now that we have that pretty clearly defined in this Venn diagram, you can do one of two things. You can either add all those probabilities up together that we just had in here, or you can use the information from up above. The probability of homeowners insurance is the 48%. Probability of car insurance is 56%. Subtract the intersection of 18%, and we get that the probability that this will happen in is 86% chance that you have one or the other with this specific company. Okay, last part at the bottom, find the probability that she or he has neither of the policies. So notation would be the probability that I have I don't want homeowners insurance, so it's the complement of H, and I don't want the car insurance, complement of C. This would actually be an AND case, and it actually would be everything that lives outside of the probabilities in our Venn diagram. If the probability you have one or the other is 0.86, that means that the outside piece here is 0.14. Okay, so you can just say it's a 14% chance. The way we can calculate that pretty quickly is by doing 1 minus 0.86. Okay. With that being said, the last page of the notes here, I want you to hit pause, try these questions on your own. I'm going to go over them in just about 2 seconds here. So hit pause. We got a multiple choice here, and then we have 2 more examples of trying to do a little bit more with mutually exclusive, and then also the addition rule for today. Okay, so go ahead, hit pause real quick. Here are the answers coming your way. Okay. For example 4, if A and B are mutually exclusive, then the probability of A or B, given the probabilities at the top, would be 1.0. If those are the only 2 events happening, the probability of one or the other, given that they're mutually exclusive, would be 100% chance of that happening. Okay. None of the others would be true, given that criteria. All right, and the next one, there are 20 climbing ropes at Merritt's climbing walls. 5 are thicker than this 8 millimeters, 4 are waterproof, and 1 is both. Probability of a rope being thicker than 8 or waterproof. So just remember, you're adding the probabilities of the 2 things together, but subtract out that intersection. It does say to try it without a Venn diagram. If you did one, I'm not too concerned about it, but just says use the addition rule. So here's my work here. Probability of a thick rope is 5 out of 20. There's 20 total. Probability that it's waterproof is 4 out of 20, but there was 1 that was both, so we don't want to double count that. Chances of this happening are 8 out of 20, or reduce that to 2/5. And finally, in the last case, actually in this last one, you would have been missing a little information, so sorry, I guess I should have given you that in advance. That got cut off there, but the sugar cone probability is 0.5. So what's the probability that the ice cream is a waffle cone or a sugar cone? Is there some information missing in order to complete this? Well, when I do that or case, I'm hoping you're thinking we got to subtract out the intersection. But is there a way for it to be a waffle cone and a sugar cone all at the same time? No ice cream place I've been to. Okay. It might exist in the world, but we're going to pretend it doesn't. So if this is the probability we're calculating, waffle or sugar, even though this is missing, that intersection, it's not needed because these two events, waffle cone and sugar cone, are mutually exclusive. So that means we can just add the probabilities together, not really worry about that intersection because there would be no intersection. Okay. Hopefully you have a good grasp of the addition rule and the term mutually exclusive now. Again, any questions, let me know, email my way. And then you'll see tomorrow's lesson. We'll start with some homework answers to homework 3. Thanks, guys. Have a good one.